So we were having a talk beforehand that this nice weather is not conducive to all of our learning, but it is going to rain this weekend. So we'll get, maybe that will help all of us, your teacher included in that. But for the IMFs, actually I can write it back on here. Again, we have ionic, which you guys know, right? You just look for metal, non-metal. We have H bond. You know, I should do this. There's a better place to do it. We have these. They're right here, right? So H bond, we're looking for the H that's attached to NOF. See, and I brought a NOF today. I'll take my headphones off to put my NOF. Maybe not. This one's a big enough one. So I realized me. The eyeballs are in the way. I never got to wear my rainbow squid last term. But since we're doing liquids, everything got quiet. Dipole just means it's polar. London is non-polar. And ionic is metal, non-metal. So that's really it. That's it in a nutshell. There's something I forgot to mention. This is on the notes tonight. So I'm like double dipping so we can get done. I'm gonna call them London because it's easier for me to call it that. But it is actually called an induced dipole because that's what's happening. And yeah, I just had to mention that. I don't know if that terminology came up. Nobody asked about it, but in case you ever ran into it, London. Last week, when we talked about this, I talked about there's so many different names for London. I don't know why they did that, but there we go. All right. So the key to doing this is identifying the IMFs. And so if this is non-polar, if it's non-polar, we're going to say London. This, we see the H attached to the end, so this is an H bond. Carbon hydrogen only is London. OH, H bond. And carbon hydrogen only is London. So that's the key. Carbon hydrogen only, non-polar is London. If you see the OH or the NH, you're doing H bond. The dipole is probably the hardest one. Anything that is London, that is non-polar, that is hydrophobic. So that was apparently A, C, and E. So it's kind of trying to tie in everything that we learned before. Sorry, my camera mirrors me and that confuses me. All right, on the next one. So you always want to do the type of IMF first, and then we're going to rank on this one. So this is London, carbon hydrogen only, H bond. So this one, if you have just an atom, so just like a noble gas or just oxygen, all it can be is London. That's your only choice. And then this one is dipole. So why is it not an H bond?
The H's are attached to the carbon.
Yes. So this is why we just did all if the H's are typically written after what they're attached to. That's why we did all the Lewis structures. Carbons make 4 bonds. You can make a quick sketch. The H's are not on the fluorine. So there is a pull. The fluorine is pulling. So that's what a dipole is. So it's saying something's pulling. They're saying 2 things. To have a pull, you have to have 2 things there. So that's why they put the di. All right. The Londons are going to be the weakest. C is going to be the weakest because it's smaller. So when you have 2 things that are London, the smaller surface area is the weaker. H bond is going to be the highest or the strongest because it's an H bond. An H bond is an extreme dipole. So if you wrote it, C is less than A, D, and then B. You're going to see this happen again where I ask you to rank them. I always go from small to largest, but I don't know, for some reason people do it the other way. To be safe that you are communicating correctly with me, just label which end is the weak end. So if you're somebody who thinks I want to do the strongest one first, then make sure you label it. So as long as you label, then our communication is going to be fine. All right, hydrogen bonds, HF, so C and D. So again, A is not, because these H's are on the carbons. They're not on the oxygen. So C and D are H bonds. So really good question that was asked before class. Why does it say in the liquid state? So tonight's lecture is about liquids. IMFs are pretty much happening in the liquid state. So the worksheet is about solids, but as a solid, they're in a pattern rigid position. And so the intermolecular forces are not going to be as important. As a gas, they have so much giggles and jiggles and wiggles. They're not near enough each other to have intermolecular forces. So the intermolecular forces are most important as a liquid. That's extra information, but if you see something worded like that, it just means that you can ignore it. This one, drawing the H bond. So you have to draw out the CH3. And the key to doing this is the OHs have to be facing each other. So on the other one, you're going to have to mirror, you're going to have to flip the molecule. And then when you show the H bond, you have to show it with dots. Lines are covalent bonds, dots are H bonds. You could actually show two of them. So that's the H bond. You have to have that strong polarity. So the oxygen has the negative and the hydrogen has a positive. And then down here, positive, negative. Mistakes that people make, you don't want to just go between H's. H bond is not between H's. That is wrong. And it can't be between any H and an oxygen. It has to be that polarized H. So these H's here on the carbon, these are non-polar H's. Carbons and hydrogens don't pull on each other. Hydrogens pull on NO and F. Why I get to wear the squid hat today. You too can wear a fun hat, a Noth, and get a bonus point. There you go. I'll put it out there. And we're back. It's after that midterm, so you guys can get your bonus points again. You can see some new names up there. That was an affirmation. See, I didn't say I want to see new names. I said I'm going to see some more new names up there. All right. Number 5. So just fluorine is London. We see the H bond because the H is on the nitrogen. On this one, H2S, there is going to be a pool. So sulfur is over in this corner that pulls. It's just not strong enough to be an H bond. So this is a dipole. You don't have to make a sketch, but it would have a bend. So there'd be a pool. And then this one is a dipole also. So the H's are on the carbons and the oxygen's sticking up there in the middle. So the London is the weakest. And the H bond is the strongest. That part, usually everybody gets it. Like by this point, it's like, okay, London I've got, H bonds I've got. The dipoles are the ones that give people trouble. So if you have two dipoles, the stronger of the two dipoles is the one that is more greedy. The oxygen is going to have a greater pull. So this has a bigger pull, so it's stronger. And again, what is pulling is the one that is electronegative. So there's a greater pull by the oxygen than here by the sulfur. It's going to be a smaller pull. So if we put them in order from weakest, I'm going to we'll put it over here. A, C, D, B. A is our weakest, and B is our strongest. All right, so more, because practice makes perfect with these. So NH3 is H bond, London. This is a dipole. So again, the question Damon answered so wonderfully. The carbon's in the middle. So there is a nitrogen. The nitrogen is pooling, which gives us the dipole. And if you see just the single element there, that's a London. Now, I do want to make a quick exception to that. If you see a metal only, that is a different category. That's on the worksheet tonight. That's why I have the worksheet, because there are some special ones. And we'll talk about that after this. So that would be metallic, and that's a separate category. But if you see just a non-metal by itself, which would be the noble gases, or just like, yeah. So the Londons, neon's going to be the weakest. So we'll just say 1, 2. This is going to be our strongest. So you can number also 3, 4, or you can make your little thing. So D is our weakest, and then BCA. Questions up to that point? And I know this is always a study set. I mean, the amazingly beautiful weather has not helped our study skills, but this is always a study set that a lot of people have some confusion with. But really, that's all there is. So hopefully, after going through this, it's like that's it. I think sometimes it's doubt that you're starting to get this. This keeps building on the polar, non-polar. The polar, non-polar is really a big concept we use the whole term. In your whole life, that's the whole thing with nutrition and stuff. All right, so comparing these two, bromine is non-polar, so this is London, and the ICL is polar, so it's dipole. So the dipole is stronger. That's all the explanation I need. You don't have to write lots of words. The next one, we have H bond because of the OH, and then this one, the oxygen doesn't have an H, so it's a dipole. So which is stronger is the H bond. All right, the next one, they are both dipole. So if they're both dipole, you have to pick one. Which one is it and why? Anybody want to get their name on the board? Which one, Major? Go ahead.
I picked ethyl oxide, propylene oxide.
The HCl?
No,
It's
I picked the HI. I was looking at.
It's actually it's the HCl. So if it's dipole, you want the bigger pool. So that's important, because on the next one, you're going to pick the iodine because of the larger surface area. So this is the question I have for you all. Why on D do I pick the larger surface area, but on C I pick the one with the bigger pool? Because once you can answer that, then you've got it.
Because D is non-polar?
On D, there's no pool. Exactly. Was that Michael?
Yeah.
My gosh, I don't think I've ever gotten your name up on the board. This is exciting. See, my affirmation worked. All right, we're gonna get more names up there. We should almost do like a double bonus if you can get your name up there before Major, because he's always like the first name up there, except he's in the coffee shop, so he's distracted. So that is really important on these two. If they're non-polar, there's no pool, so you have to look at size. If there's a pool, the pool is the big deal. That like knocks it up a whole level. All right, on this one, H2O is an H bond. So again, this is back to like C. H bond is an extreme polarity. So it just took it into a new category. The H2S is a dipole. And then the last one, we have London versus dipole. If you have two different atoms, you're going to have a pull going on there. And so the dipole questions. All right. Oh, we should connect our. So snowman goes with the ice. Steam goes with the balloons. Did I ruin it? Did you guys get that part right? Maybe. All right. You can match whatever you want. Oh, this is a question I love. All right. This is an important question. You'll see it again. So the difference between ice, water, and steam. Ice, and it's this pattern is specific to water because of the beautiful bent shapes, but for ice, you see a regular pattern. The regular pattern is true for solids. We will talk about solids on Thursday more. So regular pattern for water, the key word is what? Flow. Flow. Thank you. For any liquid, that is the key. That's why I have my affirmation back there. So you can write your liquid affirmation about flowing through life smoothly, going with the flow. It was actually my journal in Nepal, because when we were there in the monsoon season, fascinating, because monsoon rain, there's nothing like it. And so these rivers would go from these little streams to taking out a whole village. So go with the flow. And then the steam. And here, you can make a cat. What's the key for steam? Or any gas? I already said it. These guys have, if you want, you can say hi. Chaos. Who said that?
That was me, Max.
Oh, there we go. Yeah, or giggles. Lots of giggles, chaos, however you want to say it. These guys are moving, so there's lots of space between. They take up space, and so they have weak IMFs. Does ice and the water have strong IMFs? So this is back to that question on the other side when it talks about the IMF in the liquid state, because as a gas, they've lost the IMFs because of all the giggles and jiggles. There is one more piece. So questions with that. Yeah, and again, the water, the flow is the key that this moves. This next piece is only true for water. Because of the shape of water, the liquid is the densest. Pretty much everything else, except for some man-made substances, the densest is the solid. But because water makes this regular pattern, the gas is always going to be, this is true for everything, is like 1,000-fold less dense. So it's going to be the least dense. All right, questions with that?
Are we gonna have to like remember like the drawing?
What?
Or is it just for fun? Are we gonna have to like remember the drawing, or is it just for fun?
Oh,
Like
yeah,
like
drawings usually help. Yeah.
Okay.
You should.
Okay, I was just curious. I was gonna have it on there. I just thought I was going to rewrite it. Thank you.
All right. Yeah. No, thank you for asking that. So this is an important question. You will quite probably see that question again, maybe more than once. So organic chemistry, this is where it will come up again. So hexane, you guys have Google. You can just do the zigzags. So 6 zigzags is 6 carbons. Butane, I didn't say where the triple bond was, so you can put it in the middle or the end. But just a reminder, numbering, this would be 1, 2, 3, 4 carbons. So this is 4 carbons. This is 6 carbons. Butanol, we have 4 carbons, but the OL means we have an OH. So you have 4 carbons, and then on one of the middle ones, you're going to have the OH. Whenever you do zigzags, you have to show the H's on oxygens, nitrogens. You don't show the H's on the carbons. Ketone means you have this middle with double bonded oxygen, and then you have 2 carbons on each side. So this has 5 carbons. I wonder why I did that. All right, and then this is butane, and then we have a methyl. So we have 6 carbons. So it's the number of carbons was part of the key. But this OH is an H bond. And again, you can always use Google and look it up, and you would see that butanol, the OL, is an H bond. Ketone has an oxygen, so this is going to be a dipole. And the other ones are London, because they're only carbons, hydrogens. This is actually a really good study set. I'm kind of proud of myself. So the study sets used to be like today and Thursday all put together, and it was just like too much information. So, but this is a nice study set for practicing IMFs. The question that's missing from this, though, is we're supposed to rank it. And so we're going to go ahead and rank from weakest to strongest. So the H bond is the strongest. Of the Londons, which London is the weakest? Go ahead, Major.
Is it the last one? Because it has a lot of carbons and hydrogen.
No.
The first one?
Man, you got 2 strikes today. Anybody else want to take a guess? So we've eliminated the last one. It's the butane because it's the smallest. So this is going to be the weakest. It has the lowest surface area. My pen is done. So smallest surface area, which it's got only the 4 carbons. Now the other 2 both have 6 carbons. So I'm going to just put this as numbers. This is going to be number 1 for weakest. This would be number 2. Because that is a smaller surface area than the ones that are linear. This would be number 3. The ketone would be number 4. And then my strongest is number 5. And you can do that with numbers, or you can, well, I don't have A, B, C, D. All right. But does that make sense, Major?
I just been thinking of the most hydrogens, but I just put them in the other way around. That helps. Thank you.
You're welcome. All right, on these, so CO2 is interesting. It comes out linear, and so it is non-polar. SO2 is bent, so it is polar. That is actually something, I mean, it was, if you drew them, you figured that out. So if it was something like on your next celebration, I would put, you know, if you can't tell from just looking, like all the others, you should be able to tell just looking, make a quick Lewis structure. So the SO2, because it has 2 extra electrons, it comes out bent, and that makes it polar, or dipole is what we should call it. And so the dipole has the stronger one. CF4, this is going to be non-polar, and this is going to be polar. So London versus dipole. If I ask you to tell me the type of IMF, the words would be London and dipole. Again, you can make a quick sketch. but this one has that fluorine. But keeping in mind, this is why you did that organic lab. Carbons make 4 bonds, so this is a carbon surrounded by 4 of the same thing. So even though the fluorines pool, if they're all fluorines, they cancel each other out. The next one, they are both nonpolar. So then we pick the larger one, greater surface area. Sometimes I do ask you to explain. I mean, here you don't have to because they're different, but that's all you have to say is greater size, or it's really greater surface area. And then on this one, they are both ionic. So it is the magnesium oxide. Any idea why? Major's like throwing up his hands. He's like afraid of striking out here. Anybody want to help him? I never taught you this, so it would be awesome. It would be definitely worthy of being on the board. But any idea what you need your periodic table?
Is it because they have higher charges?
Yes. So it's actually Coulomb's law, which if you read, it talks about that. But in physics, you learn about Coulomb's law. Magnesium and oxygen have charge of 2, and the sodium chloride have just a charge of 1. So +1, -1. You would only do this if they're both ionic. The greater charge difference gives you a greater attraction. If you have 2 things that are polar, you're looking for a greater pool. And if there are 2 things that are London, you're looking for greater size. I didn't talk about that one last week because we had enough information. Any questions?
All right, yeah, I have a quick question. So do we only count the surface area to see which one is stronger? Only if they're both nonpolar.
Yes. Only if they're both London do you look at surface area. Exactly, because otherwise there's something that has happened with charge. And so that polarity or the charge makes all the difference. That's much bigger than surface area. So London is really weak. It's extremely weak. Most things that are London are gases because they don't have enough traction to pull them into the water, into the liquid state, sorry. All right, phase diagram. Solid, liquid, gas. That is the key. I should have done that in a different color. So solid, liquid, gas. As you increase the temperature, you go from a solid to a liquid to a gas. So the triple point is right there. It's where all 3 phases exist. And again, they have found many more states of matter. We're only going to deal with solid, liquid, and gas. But there are at least 9, and there's probably infinite number of states of matter. We think very 3-dimensional in science, and there's probably infinite number of dimensions. And so if you can take, that's where meditation comes in. That comes back very soon. So negative, this is what X before Y, you guys learned that in math. And this is like at 6. So if you gave me that as an answer and it was a test, celebration, whatever we can call it, or a worksheet, you wouldn't get full credit. What's missing?
Units?
Units. You got to have units. We're going to be getting back into math. On Thursday, you got to have a calculator. We do the heavy dutyest math, and all next week is math. Next week's math is easy math. I saved gas laws for last because they're really easy. That was the start of chemistry, gas laws. So degrees Celsius and ATM. The boiling point. So boiling point means liquid changing to a gas. So you can all figure that out. So then you find 30 and you try to make a straight line and you go across and you come down. So it's looking like it's 50 degrees Celsius. The densest phase is almost always a solid, but you can tell that if you picked at 0 degrees Celsius and you increase the pressure, you eventually are going to push it into the densest phase because you're pushing the pressure, you're pushing it together. Water, again, is special because the solid, when you push it together, it starts flowing like this. It has to do with that bent shape, the 104.5 degree angle. All right, and then you have to have your solid, liquid, gas. If we go from A to B, That is going from the gas to the liquid. That is condensation. This was on the last year's midterm. I was looking for a good question. B to C is liquid to solid. So that is freezing. And then C to A means we're down here. This is where you go from a solid to the gas without becoming wet. And so this is sublimation. And again, other than in this class, you're probably never going to read a curve like this, but you're all going to have to interpret graphs. So approach the questions. We're going to see more graphs today. That in life, you're going to have to analyze graphs. They show up, especially you're going to medicine. It's all in statistics and all that. All right. So number 12 goes with the worksheet tonight. It used to be a question on the worksheet, and I got tired of having to correct everybody. So we're going to do it together. So covalent bonding, what's the difference here? So covalent network solids. So your worksheet tonight was here. There's a video that goes with this on YouTube. It's like 16 minutes. And I do the top part up here. And so this top part is like where you're taking notes. I just need to see it's filled out. And down here, you're going to determine. But there are some categories that were not intermolecular forces. So we talked about ionic, polar, and nonpolar. I should have put metal is a special category. So metallic. There's also a couple of pages that has some words if you prefer words. But it's this, the macromolecular is one huge macromolecule. So covalent network is also called macromolecular. It is all covalent bonds. Again, it is your shoulder attached, your arm attached to your shoulder. You can't get rid of it just by shaking or doing whatever, jumping up and down. You're going to need a chainsaw, which is not a pretty idea, or a laser or something. A lightsaber would do it. The molecular ones, and so because of that, on these, they're all covalent bonds. They have extremely high melting points. There's no attraction. They're all stuck together. So it's all one molecule. That's kind of, right? The hippie theme. We're all one. Molecular, they have individual molecules. Like our water that we drew at the top of the page. Each one of these is an individual molecule. Even here, there's a gap. And so there'd be an attraction. The orange is the attraction between them. So these have an attraction. That's why they're there. But there's an attraction between the molecules. So you have individual molecules. In the molecule, you have covalent bond, but they're held together by IMFs, or they're attracted. They're not held. They're attracted to each other. IMFs are just attractions. You can jiggle apart. You cannot jiggle apart. This is like holding hands with someone. You can jiggle it apart. You cannot jiggle apart a covalent bond. So an example that I talk about, this is diamonds, is the macromolecular. Sand, so every grain of sand, that's a whole bunch, or what's running your computers, the silicon dioxide, my crystal that I wear, which is, yeah, it's all one big macromolecule. So like what Kobe's going into, you'll run into a lot of those in geology. Questions from the study set? All right. I want to mention real quick the worksheet while we're here is, so the top half, you watch the video, it's 16 minutes, or you can read them from, and you just fill in. The top part is kind of like taking notes. And then down here, this is what the gnomes did. They just didn't do anything. You pick the category and you tell me what of over here told you that category. And then only some of them you should do another test to make sure. I will tell you this, M, there are two possibilities. So you need another test. So M is probably, we have an idea, but part of it has to do with that metals have quite a range of melting points. So sometimes they melt, sometimes they don't. All right, and then you can read my story too. Any questions before I stop this one?